the topic of the presentation for the next one is the simulation the contact interaction of the needle and brain tissue by Professor Lycheva.
Good day, dear colleagues. In our short communication, we'd like to present some results about modeling of the contact interaction of the needle and brain tissue. This problem appears in the modeling of biomechanical problems, which relates to some medicine problems and processes with interaction of brains and some medical instruments. So what we want to model? Firstly, I'd like to underline the general idea. We model brain as a half sphere with outer layer. The mechanical properties of outer layer differs from the mechanical properties of the inner part. And in inner part, we have soft tissue, while outer layer is more harder. And we have needle that penetrates into this system. And during the penetration, we can control the process by applying forces on the end on the needle. Here you can see three components of this external interaction. The force P that press the needle and by this force, the needle penetrates into soft tissue. The force F and the moment M, by which we can control the process and make some bending of the needle, and by this we can change internal deformations and internal stresses in all systems. While penetration, the stresses appear in the interior part of soft tissue, and due to these stresses, the shear stresses appear on the contact between needle and the tissue. And of course, we feel some resistance for the penetration. How we can describe this resistance? We suppose that this resistance appears to be the sum of two factors. The first one is the resistance of penetration that relates to some fracture of the tissue. And the second is some resistance that appears to be due friction and adhesion on the cylindrical boundary of the needle. So it's important now somehow to take into account these factors and to model the mechanical process of the penetration of the needle into this biological system. How we can do it? Of course, this problem is complicated, and in order to make some simple approach for this problem, we study more simpler one-dimensional prototype model. In this model, we take into account the needle as the beam that can bend under the forces that apply to its right end. And left end penetrates into rheological media, and in this media appears some compression stresses due to its viscoelastic properties, and some resistance which is applied on the part of the beam that penetrate into a rheological system. We model the interaction between the rheological system and the beam with the beam equation that have additional terms that relates to some elastic foundation and viscoelastic foundation. And due to this modeling, we can obtain the distribution of the stresses, normal stresses that apply to the boundary of the beam. And due to these stresses, we can calculate the resistance shear stresses that appears due to penetration. Then we can calculate solve the equations that describe the movement of the whole system, and obtain the distribution of stresses with respect to given scenario of penetration of this beam into a rheological system. In order to implement this program, it's important to obtain the solutions for the bending beam and the solution for the interaction process. How we can do it? Fortunately, we can obtain the solutions in analytical form. I like to describe this solution step by step. Firstly, we can take into account only elastic properties of the media in which the needle penetrates. And so it's important to solve the problem of the beam that can bend, and the part of the beam interacts with elastic foundation. We can change the length of the part that interacts with elastic foundation, but this length is only the parameter of the problem. We obtain a very simple solution in engineering manner in terms of elementary functions, and we implemented the solution in Mathematica, and we can see how it works. So here I change the penetration depth, and we see that we can obtain different distributions for displacement of the beam and for internal stresses in the beam, and of course for internal stresses in the media. Then the more complicated problem is this viscoelastic one. Now this problem is described by a partial differential equation that depends on x and on t. And we can apply the separation of variables for this problem and obtain the solution which depends on time in terms of series. Here you can see the solution for some moments of time for some fixed penetration depth. Here penetration depth is also the parameter, and we can change this parameter. For example, here we make it more greater, and also we can model the dynamical process of the distribution of stresses. It's not a really dynamical problem for penetration because the penetration depth here is fixed. Now it's important to passage to more complicated problem where the penetration depth and the bending of the beam both are dynamical parameters and they both change in time. So we have now the problem with varying domain. And this problem we also can solve in analytical manner. By changing variables, we can transform the non-constant domain of the problem to constant domain, and apply also the separation of variables. We can do it here, and here you can see some results of this analytical solution. Here you can see that the penetration depth and the bending changes in time. This is a fully dynamical problem, excuse me. And with this problem, we can model the process of penetration into viscoelastic media, and we can obtain the distribution of forces that apply to the boundary of the beam, and with them we can calculate the distribution of resistant forces that appears in soft tissue and that apply to the needle. And now we have everything, and we can calculate the total overall force that resists, that gives the resistance for the penetration of the needle, and obtain the fully dynamic of this problem. Here you can see some results, and we model here the penetration of the needle into a two-layer soft tissue. After penetration of the outer layer, the force reduces to some value, and then it evolves also in time. Here you can see on the vertical axis dimensional penetration force, and horizontal axis denotes dimensionless time. And of course, this results is very model. We obtained these results with some parameters that we take from the air. In order to obtain results that corresponds to a realistic biomechanical process, we have to identify the parameters of the model. And here, I would like to make some conclusions for our presentation. Firstly, I'd like to underline that the results of the test calculation are in qualitative agreement with physics of the process. Then I'd like to underline that the model contains sufficiently large number of parameters. For example, we can take into account the changing in time of the control forces, control moments, and we can take into account changing in time layer by layer the features, mechanical and viscoelastic properties of the tissue in this system, biological system. And of course, in order to obtain more realistic results, it's important to identify these parameters. Now, I'd like to mention also that all these results obtained for some prototypical problem, where instead of a three-dimensional needle, we took into account one-dimensional beam that penetrates into viscoelastic media, maybe lead viscoelastic media. Now, what we have to do, we have to implement fully three-dimensional case and take into account all three-dimensional features of this problem. Thank you for your attention, and we will answer on your question with pleasure.
Thank you, Professor Lycheva. Is there any question that on
Thank you very much for very interesting presentation on the results. And my question is, if it's possible to model the elastic instability in the process of indentation based on your model?
I think so, but in order to understand the instability, we have taken into account some nonlinear properties.
Mm-hmm.
So it's interesting problem, and it will be interesting to try to solve it. But at the point we have achieved already, we took into account only elastic properties.
Mm-hmm. But very interesting. I like your results. We will discuss later.
With pleasure. Thank you very much. Thank you.
If there is no question, thank you, Professor Lycheva, for your very exciting presentation.